Yesterday we talked about finding the sum of a finite geometric series. Today we are going to find the sum of an infinite geometric series. Okay? So this is not the formula. This is the formula you used yesterday. Hopefully that looks familiar. We're going to work with that formula to figure out how we can come up with the sum of an infinite geometric series, which for those of you that are a little concerned with that, you're like, hold on, how can you find the sum of something that's infinite? Okay? You can. Okay? All right. So what I'd like you to do right now is I want you to take that formula and I want you to do some stuff here. When you substitute a value between 0 and 1 for r and raise it to the nth power, what happens to the numerator? Figure that out by trying to plug in 2 for n, 3 for n, then 4, then 5, then 10, 100, 1,000. Okay, keep plugging in bigger and bigger numbers for n. What happens to the numerator? Okay, and then you should be able to answer that in question there. How does that change the numerator of this formula, which we use for a finite series? Okay? So, let me explain what's happening. When we're putting in a bigger number for n, hey, why is there all this talking going on? If you're talking, you need to come up and start teaching. Okay? Hey, if we're plugging in bigger and bigger numbers for n, then n is increasing. We keep going. I mean, you could put in the biggest number you can think of for n. Okay? What you should start seeing is a pattern. All right, so what I want you to do is keep plugging in bigger numbers. Remember, n represents the term number. So when I put in 20, I'm talking the 20th term. When I put in 1,000, I'm talking the 1,000th term. Okay, the sum of the first 1,000 terms. Right? That's what we're doing there. Okay, we're just going to focus in on this chunk of it right now, though. I want you to find out what happens to the numerator as you increase n. That's the only part that has n in it. So, how many of you used a different ratio than someone around you? Okay, what did you guys come up with? What did the numerator become? 1. Okay, so I have Emma's calculator here. She used 0.5. Okay, she put in some really big numbers. Okay, bit smaller numbers. Okay, and no matter what, she put in the really big number there. She got 1. All right, so how does that change the formula then? Yeah. Good. Yes, your sum would become a sub 1 over 1 minus r. So the sum of an infinite series is that. Nope. Okay, now remember, there's some rules here. R, it's actually the absolute value of r, has to be less than 1. Okay? The absolute value of r has to be less than 1, and, well, not and, I guess. If the absolute value of r is greater than or equal to 1, it does not have a sum. Okay, so remember, we're putting in a value right here of 0.5 for r. If I kind of go through this same process that Emma's went through here, and rather than putting 0.5, maybe I just copy that equation and I put in 2. Okay, I get a huge number. Okay, and remember that's scientific notation, right? It's 1.09 all to the 12. In other words, I got to move my decimal 12 places. That's how big that number is. It's a huge number, and that's not even a huge power. I mean, it's 40. We didn't even use the power up here Because it would be, what would end up happening is you'd have an overflow. Your calculator couldn't keep track of it. It's too big of a number. So what would happen, make sure we're clear on what happens when you put a number bigger than 1 in there. This numerator is no longer 1. It becomes a big, big, big number. And when you divide a big, big, big number by a smaller number, and remember this will have to be smaller because this has a power. It's the same. This is to the first power and that's to the nth power. When you take a big number and you divide it by a small number, you get a bigger number. Okay, you get something bigger than you started with, right? Okay, or not bigger than you started with, but you get something bigger than 1, which here you're getting a portion of what you started with when you're dealing with n. Okay, so that n right there, remember n represents how many times or what term of the pattern you're on. So like the first term, the second term, the third term. This is saying the sum of an infinite number of terms is equal to a certain value. It approaches a certain value. It is limited to a certain value. It does not mean that the number of terms terminate. You have an infinite number of terms. Okay? But it will approach an amount because you are just adding fractional pieces every time. N keeps on going on forever. Yeah, it would be an infinity. That's why you wouldn't need it, correct. When we do our arithmetic? No. We're with only with the geometric. Okay, so get that formula down. I want to show you how it ends up graphing here in a minute. Okay? All right. We good there? If you turn to page 233 of your student journal, they actually have the formula right there for you. It wasn't as... That's pretty anticlimactic when you do it that way. Okay? So let's skip that page and move on to the cool page, page 234. Em, I'll get your calculator back here in a minute. But if you guys, please look at the bottom, or problem number 2 is the one I really like on this one. Okay? It says, in exercises 1 and 2, consider the infinite geometric series. Then find the graph of the partial sums. The reason it says partial sums means you're taking just a portion of the series. So they want you to graph just these sums. Then describe what happens to S sub n as n increases. So find the partial sums for 1, 2, 3, 4, and 5. In other words, what they're saying is if you make a table, there's some confusion the first class on this. Thank you. So if you make a table, n and S sub n, okay, if I am taking the sum of the first term, that should be pretty easy. You look at the first term and you say, okay, it's 3. However, the sum of the second term, well, that means the sum after the second term is the way I should say that. The sum after the second term would be 3 plus 3/5. So you added 3/5 to that. That gives you, and I'm going to put it in decimal form, 3.6. Okay, what I want you to do is I want you to find what the sum is after the third, after the fourth, and after the fifth term. Okay. And then let's graph that. Let's go ahead and define our axes here. Poor job at drawing that. But there we go. We call this, let's go by halves. Just so we're all on the same page in that sense. Okay? Okay. So after the third term, 3 plus 3/5 plus 3/25. An easier way to think of that would be just saying 3.6 plus 3/25. right? Which is how much? 3.72. Yes?
So like with the decimal, you're kind of like, it's almost like you times something like 2, but like so this is 0.6 and then 3/25 is 0.12.
Okay. I see what you mean. Theron, what's your question? Have you done the graph yet? You know a good way to figure out what the graph will do? Is complete the graph. But, hey, if you didn't complete the graph yet, we're about to find out. Notice we are approaching what number? 4. It's kind of hard to tell what we're approaching. I mean, like, what if we're adding smaller amounts. What is 3 divided by 625? So this number right here is 0.0048. So really, really small contribution to that, right? So it doesn't change it a lot, but it does bump it up over, so we have to round up to 3.75 now. Okay, so if we keep adding a smaller and smaller and smaller amount, I mean, we started with 3. We went to 0.6. And then we added 0.12, and then we added 0.0. What do we have there? 0.0224. Oh yeah, and the 48. Okay, so we kept getting smaller and smaller that we're adding. Is this number going to get much bigger than that? No, that's why you can have an infinite number of numbers in a sequence, but it approaches a finite point. Okay? Because it's such a small amount that's being added. Okay? So as you graph it, and I'm not going to re-graph it, I have it here. But, hey, the sum appears to approach 3.75. How could we verify that? We could actually use our formula and see if that's what it approaches. A sub 1 was 3, or is 3, and we are subtracting we're dividing by 1 minus r. What is r here? We're multiplying by 1/5 every time, right? So 1 minus 1/5, I automatically go to 3 over, how many fifths do I need to make a whole? 4. If I'm at 1/5, I need 4, so that's 3 divided by 4/5. Which is it's not 0.75, I'm sorry. It's 3.75. Okay, which is, as Riley said over there, 15/4. Okay. I like fractions better too, Riley, but for this case, decimal worked well. That should be a 3. All right, 3.75 or 15/4. Okay. Questions? I know I'm using a pen. Mr. Kolstad would not be pleased. All right. That was my teacher. Okay. Any questions? Everyone understand pictorially what we're getting here? How we're doing this? Okay. That's kind of the key. Actually, literally, that is the key. I know. Oh, I know. All right. Why don't you take a look at the next page, page 235, complete 3 and 4 with your grouping. All right. I have located my pencil, so I won't be using pen. Find the sum of the infinite geometric series if it exists. Does one exist on number 3? How do we know it exists? Because r is less than 1. And first we have to actually recognize that this is our rate right here. What's this number? That's a sub 1. Yeah, this is r. Okay, r is less than 1. Now remember, it can technically be between -1 and +1 because the absolute value of r has to be less than 1. So we just explored between 0 and 1, but it can technically be between -1 and 1. Okay, so this right here, 3/5, if we're using it to find our series, we have S is equal to A sub 1, 1 minus R. A sub 1 is 6. So being able to recognize that, minus 3/5. Or some of you will just jump right away to that being 2/5. 6 divided by 2/5 is 30/2 or 15. Total, yeah. Okay. Number 4, does it exist? No. R is greater than 1. There's no sum. Sum does not exist. Just keeps getting bigger and bigger and bigger. Okay, I want you to try numbers 5 and 6. If you have questions, ask me as I'm walking around, please. Here we go. Let's check them out. Way to succeed.
I'm a good person.
Hey, if you didn't get it, doesn't make you a bad person. Just means you missed. But you're still a good person. Because you're wearing your square root of the answer shirt. Nice work. Okay. Questions? All right, number 7. Move on to 7. Skip 8, or hold on for 8 for a minute, but go to 7. Okay, tell your neighbor what you got. It is 120. Yes. So we have to first recognize that A sub 1 is 30. First swing, and then it changes 3/4 every time, which is 75%. Okay, plug it into your equation. You get 3/4 minus 1, or 1 minus 3/4 is 1/4 of your denominator. Gives you 120. All right, the last part I think is cool, this last problem. And I used to just show this just for fun. I am not going to spend the time in class right now to explain why it works, but I will show you in the book where to look. And it gives a good good explanation, I think, or a decent one. I want you to have some time to work and ask questions, especially since I won't be here tomorrow. Okay? So, if you have a repeating decimal, you can take, how many numbers repeat here? 2 numbers. You take those 2 numbers and put it over that many 9s. That is the fraction form of it. Okay? So if you didn't know that, all repeating, yes. So let's finish this one first. Simplest form, divide by 3, you get 4/33. Now, if you put 4/33 into your calculator, you actually get that if you think I'm just like lying to you or something crazy like that. Okay. So let's say for instance you have 0.793793793. How many numbers are repeating? 3. You divide by 3 9s. Yes. So the inquisitive mind will say, the inquisitive mind may go like, why is that? And it does have to do with the sequences. Okay, this is your actual, this is in your book. It's on page 438. It's example 4 if you want to look into it and actually read a bit more about it. But for instance, they went with 0.24, 24, 24, okay, it's repeating. So 0.24, 24, and so on is 0.24 plus, you put zeros where those were, another 24 at the end, plus now you have 4 digits. So now another 24 at the end. Everyone see how that's repeating? You're just adding 2 more zeros to the front every time. You're just adding 24 to the back. Okay? So 0.24 plus 0.0024 plus 0.000024. That's what they're doing here. So the sequence you're looking for, you're taking this and dividing by that. That's your ratio every time. Okay? That's what's happening right here. So you're multiplying by 1/100. So to find the next term in the series, then you could use this formula. Okay, since your ratio is in between, or it's less than 1, you can say a sub 1 plus 1 over r, or 1 minus r. A sub 1 is the 0.24. 1 minus r is 1 minus 0.01, which is 0.99. That's where that 99 comes from. So 0.24 divided by 0.99 is the same thing as 24 over 99. So the quick process, like if you're like, oh, okay, I'm following along. Well, the quick process, just take the numbers that repeat and put it over that many nines. Okay? I don't ever, when I show it, I might go through that process, but I don't ever do all this other stuff on my paper. It's good to know why it works. It's good to see how it relates to what we're doing, but it's the quick way to remember it is however many repeat, just put it over that many nines. Okay? Questions there? Just out of curiosity, how many repeat on number 6? 1, right? So it's just 5 nines. Okay, so you should automatically know all your nines now. 1 ninth is 0.1111. 2 nines, 0.33333. 3 nines, 0.44444. Right? What? Yeah, 4 nines, 0.44. Oh, okay. 5 nines. Okay. 6 nines. 7 nines. Come on, stay with me. 8 nines. Come on, stay with me. 9 nines. Oh, hold on. Isn't it that? Hold on. You're supposed to continue the pattern, right?
No, you're breaking every single law.
I'm just saying. Hey. Oh. Isn't that great? Man, I love it. Okay, 9 ninths is actually 0.99999999999, which approaches 1, which is what we've been studying all today. Isn't that great? Woo! I love it.